let's just record for this week, see how it goes. Okay, so previously, the first 3 sections, yeah, question, Leah?
I was gonna say it might be like more helpful just to upload like the notes with all like your writings. It might be like easier to like go through it instead of like having to rewatch the entire lecture.
You don't try to use the fast forward, because usually the notes is actually kind of like also shifted, so the writing's even like wonky.
Well, it's just like easier like if I'm going through to like solve problems, like going through your notes and just like
Okay.
scrolling.
Okay. I can upload both of them, and that way you can have both. Okay. Yeah, it's pretty. It might not look great. Okay, but the notes could be accessible. Okay. So the first 3 sections of the chapter was about this idea of there's these 2 things called charge, right? And then we learned it's actually these things called electric charge, right? They used to be called glass charge and plastic charge, but then we figured out that the glass charge is actually positive charge, right? Which is associated with the nucleus of the atom, where the plastic charge is the negative charge, which is associated with is from the electrons in the atom, right? And previously people didn't understand, in the 1800s, people didn't know about atoms and stuff like that. So they just assumed that it's the positive charge that's moving around, right? And now with our modern day knowledge, we know that's not true typically, at least on conductors and on solid. If you're doing chemistry, right, you may have these hydrogen ions moving around, which are positive charge moving around. But right, if you were to plug your computer into the jack on the walls here, the protons / nucleus are not moving around. It's actually only the electrons that are moving around, right? So the electrons are actually the mobile charge carrier. And that's the idea of the charge model, where, right, we have some sort of positive charge, which is usually the nucleus, okay? And it's immobile. They don't move around, mobile, okay? And then you have these electrons, which are actually the mobile, right, charges that are able to move around. So typically, if you were to rub a piece of plastic with a wool cloth, it's actually the electrons that are being transferred onto the plastic, and then the nucleus just kind of stay in place so they don't move around that much. Okay, and having a positive and negative charge near each other, right? We actually found out that they would exert an attractive force between them, right? If you have 2 negative charges near each other, they would exert a repulsive force, right? Right. And today we're going to learn how someone, well, namely this guy, that's why this section is called Coulomb's law. This guy, Charles Coulomb, probably looks like a French name, right? Actually figure out how strong that force is, okay? If you know the amount of charge, the amount of positive charge, the amount of negative charge, you can actually figure out how much these 2 charges are going to be attracted to each other, how much force is going to be applied. And you can actually see the device. He's actually holding it here with this. He probably has to hold it for like a few, multiple days, multiple hours, because this is a painting of a person. People used to have to sit for days just to have someone paint their likeness. He's so proud of his little device. He's holding it while someone painted his portrait. There's a schematic here on the right, okay? And those of you who had, I think in general physics 1, I did mention a little bit of it. The idea, the way this little device works is that he was able to hang a little bit of charge inside a tube. It's not a vacuum tube, but the reason why he put it into a glass tube is so that there's no wind that's going to be like, there's no draft that's going to cause it to move by itself, okay? Basically, it just hangs there. And what they did is he added some charge onto the inner part, right? Either positive or negative. And then he had some other charge that are moving around. And then he was actually able to measure as a function of distance apart from each other, how much force is actually being applied to these little metal balls that he charged up. Okay. And if you know how much acceleration and how much mass that object has, right, then you can calculate the force on it, right? Because just the mass times acceleration tells you the force. And that's how he actually was able to come up with Coulomb's law, which I think we'll just state here, okay? So Coulomb's law states that, right, if you have two different charge 1, charge 2, they're gonna apply equal and opposite direction force on each other, right? It's just the same idea of Newton's third law, right? Where, you know, if I was to push Anthony, Anthony will push me back with equal and opposite force, right? So they're going to be equal and opposite each other. The way we calculate this is basically by figuring out how much charge is on charge 1, you know, little metal ball 1, and how much charge is on metal ball number 2, okay? And the force decreases as the further apart they are. In fact, they decrease with the distance squared. This R is the distance between them, okay? And he came up with this constant, K, in order to signify what will be the conversion factor between charge and force, okay? In fact, I think his measurements of this was like within like 5% of what we have today. So it's a pretty good measurement even back then, right? Considering, you know, he probably had to build this little glass tube, right? So this K constant is 8.987 times 10 to the 9. So it's a pretty big number, right? Okay. And has units of Newton meter square per Coulomb square. Remember this C stands for Coulomb, which is the units for charge, right? The base units of charge, right? If I tell you something that has 10 coulombs of charge in it, it basically tells you how many lack of electron it has, okay? Okay. If you're just doing calculations to 2 sig figs, you can just use 9 times 10 to the 9. This is a much easier number to remember. But if you're doing anything beyond that sig fig, then you probably have to take this whole 4 sig fig number and do your multiplication that way, okay? So this constant, the book calls it the electrostatic constant. I typically don't like this word because there's also another constant called the electric constant that we're going to learn about in a little bit. And that's actually a very different number, okay? So electric and electrostatic, those can get mixed up sometimes. What most people say is just the Coulomb constant, okay? That's what the big K is, okay? So we'll refer to that in class as the Coulomb constant, but when you read it in the book, it'll say electrostatic constant. It's the same thing, okay? So just like our charge model, right? If you have two of the same charge, they're gonna repulse each other. If you have opposite charges, they're gonna attract each other. So we're gonna see a picture of this right now, okay? So let's say you have little charge metal ball 1, charge metal ball 2. If they both have positive charge, they're gonna try to repel each other, okay? And if they're not, you know, just horizontally oriented like this, right? Let's say one is a little bit higher, right? The force that they're acting on each other are going to be these force vectors, right? Okay. And in 2 dimension, these force vector F1 on 2, right? Just to remind you guys how these notation work, right? When the book writes F1 on 2, a shorthand on this is actually F12, meaning some object 1 is acting on object 2. So if I was to push, sorry, I'm using Anthony as an example all the time, right? If I was to push Anthony, it'll be force of Dr. 2 on Anthony, right? So it's force of well, my first name is Wayne, so W on A, okay? So this is the force provider, and this is the object that we're moving. This is the object, okay, and this is the source of the force, right? Okay, and notice that, you know, it doesn't have to be horizontal or vertical. It could be some vector in this plane, right? So, and R is the distance between those two things, and R gets a little complicated, right? This is also a vector. I don't like the fact that they put this as just a distance, right? This is technically a vector between these two charges also, okay, which has an X component, some Y component, and then we have to figure that out, okay? And we'll do an example of this, I think, in the middle of today's lecture, okay? If they're both negative, of course, the same thing happens, okay? They both repel each other. Only when they are opposite charge, the two charges will attract each other, just as you expect, okay? If we have more than two charges around, so notice that when you have two charges around, there's one force, right? So there's the charge that's applying the force, and there's the charge that is receiving the force, the object, right? But if you have like three charges around, let me just do a little drawing here. Right, let's say you have some positive charge, some negative charge, another positive charge here, right? These charges, let's say call this 1, 2, and 3, right? Charge 1 and 2 both will apply a force to charge 3, right? In fact, the force vector of this will be, oops, I was trying to do red, right? We'll be pulling this way, we'll be pulling it this way. This one is called, what should this bottom one be called? F what? What should be the numbers? I'm sorry? 3 on 2. Well, I'm having charge 1 and 2 pull on charge 3. So what should be the first one? 2 on 3, yeah. So, or simply just 2, 3. Okay. How about this one? Force, what should be numbers on bottom? 1, 3, right? Because the object that we're pulling on is the second index, okay? Okay. Since these are forces, right? When you have two forces, you can add them vectorially. In this case, it kind of looks like they're gonna be like kind of horizontal. This is the net force on charge 3, right? So therefore, when you have multiple forces acting on an object, just like in general physics 1, you have to add those forces up as vectors, okay? Right? So there's some X component here, some Y component here, right? They have to add up, okay? And we'll do a little example of that in a little bit. So the way you figure out how to solve these Coulomb forces problem is, of course, I'm gonna have you guys always draw a picture, right? And we're gonna see some pictures of this and create a coordinate system. So meaning an X coordinate or Y coordinate, to everyone makes sense, okay? And then what we're gonna do is we're gonna apply Coulomb's law. This Coulomb's law kind of basically just gives you the magnitude, right, of the force, right? Okay. Notice that these little bars are absolute value signs, right? It doesn't actually care what the sign of the charge is. It gives you the magnitude, but from the drawing up here, right, this example up here, right, from those drawings, you want to figure out what the direction is from the drawing. You don't want to figure it out with some complicated equation, right? A drawing is much easier to understand than the long sets of vector equations, right? So make sure you're figuring out the direction with the drawing, okay? Let's see what else they wrote here. When possible, use a graphical vector addition in the drawing. So it keeps saying, just draw these as vectors, okay? And with each force vector, break it up into this X and Y component and then add the components, right? Remember back in general physics 1, when you have, force vector 1 plus force vector, let's not call it 1 and 2, A and B, right? In order to add these two vectors together, you have to get the X component of A added into the X component of B in the I hat direction, all of that, plus the Y component of A plus the Y component of B, right? And then that's in the J hat direction. You add the components, right? That's the only way you can add vectors mathematically, right? You don't add the magnitude, you don't add the directions, right? You only add the components, okay? And then you do your, your unit check, your stick check, and we're gonna hopefully get the right answer. So with this little technology, let's see if we can do a little example here, okay? So we have two plastic beads that are rubbed by wool. So if they're both rubbed by the same thing, they're probably gonna develop the same type of charge, right? Either positive or negative. Bead number 1, on the left develops a charge of negative 1.6 times 10 to the negative 9 coulombs, so pretty small amount of charge. In other words, negative 1.6 nanocoulomb. This little n stands for nano, right? Nano is equal to 10 to the minus 9, right? Okay. The bead on the right develops a charge of 4.2 times 10 to the minus 9, or negative 4.2 nanocoulomb, okay? These beads are held 1 centimeters apart from each other along the x-axis. We have to find the magnitude and the direction of the force that bead number 1 is exerting on bead number 2, okay? So let's see if we can do the physical drawing. So this is usually the information gathering part. Let's just try to do the physical drawing, right? Okay. So we have, 2 beads, right? Let's call this 1 and call this the one. Number 1 is on the left, number 2 is on the right. And the problem tells you it's on the x-axis. So the x-axis is actually somewhere along here, okay? Okay. We don't know where the origin of the x-axis is, but maybe it will not be relevant anyway, okay? So charge number 1, right, has a charge of negative 1.60 nanocoulomb. Charge number 2 has a charge of negative 4.20 nanocoulomb. Okay. And the problem also tells you that these are held 1 centimeters apart, right? Okay. Instead of writing 1 centimeter, what would I write? Well, just not. I'm going to write the number anyway, but instead of writing centimeter, what should I do right away when writing down numbers from the problem? Convert to SI units, right? Yeah. So 1 centimeter is 0.01 meter, right? So I don't want to, as soon as I see a number that's not in SI units, I convert it right away. So I don't have to think about it anymore, right? So once everything is in SI units, right? You just plug in the calculation. You don't have to do unit conversions anymore, right? So do that as soon as possible. Okay. So, right. So what we're trying to figure out is try to figure out the force bead 1 is exerting on bead number 2. Since they're both negative charge, right? And we're trying to figure out what is the force on bead number 2. Let's highlight it here, right? Which direction is going to be the force applied to? The positive or negative x direction? Positive, right? Because they're going to push each other apart, okay? So let's do the little force drawing. Let's just do that in green. Right, this is going to be force that 2, oops, I did it backward, right? 1 is going to exert on 2, F12. Okay, the magnitude of this, right? So without the vector on top, it's going to be this Coulomb's law, K times Q1, Q2 over R squared, right? Right, and K is 8.9, see, 987, I think. Yeah, 987. It's not an interesting number. You just count down from 9. 987 times 10 to the 9, right? Since we're doing this the first time, I'll write down the units just in case. Okay, charge 1, we're just concerned with the magnitude. Okay, 1.6 times 10 to the negative 9, and I'll write down the units since we're doing this calculation the first time. And then charge number 2 is 4.2 times 10 to the negative 9. Both have coulombs. The two factors of coulombs actually cancel each other out, right? And the distance between them, right? I'm looking at this is 0.1 meter. Okay, the whole thing's square. Okay, since this meter is squared, right? Right, that meter is squared, so they should cancel out also. Okay, so the result here, I have my calculator. Okay. 8.978 times 10 to 9 times 1.6 e negative 9 times 4.2 e negative 9 divided by, oops, divided by, don't forget to square this, right? 0.01 squared. Okay. And the force you're going to get is 6.04 times 10 to the negative 4. And the only unit left over is Newton, which is in fact the units for force. Okay. Okay. So this gives you the magnitude, right? If I want to write the full vector notation of this, okay, what should I write? 4.06 times 10 to the negative 4 Newton. What am I missing? The direction. So the direction is in a positive x direction. So there's actually the I hat direction, right? So that's the full vector answer. Okay. Any questions about this example real quick? Okay. Hopefully people are also checking my calculations. I know those of you who had me last semester know that I usually make a mistake when I punch in numbers in the calculator, right? Okay. All right, let's do a little quick kind of wouldn't call it a poll, just kind of raise your hand. Right, so let's say I have two charged spheres, A and B, okay? They're gonna exert a repulsive force on each other, right? Because they're both positively charged, okay? So if the charge on A is 4 times bigger than the charge on B, so meaning the bigger sphere has a much bigger charge, how does the force between them compare? Okay, let's give you guys like 10 seconds to think about it. Okay. So there is A on B going to be bigger? Are they going to be the same? Or B on A is going to be bigger? What do you guys think? Okay. Anyone thinks it's A? Okay, so A is going to exert a bigger force on B. Okay, so a few of you guys, who thinks that they're the same? Okay, 3, good. Okay, who thinks is B is going to exert a bigger force on A? Okay, who has no opinion? Okay, the rest. Okay, so those of 6 of you who answer, who raise your hand, thanks for doing that. And it's a really good exercise just to, it's not to, you know, oh, you raise your hand, you got the answer wrong, right? But to just so we can get a gauge of like what people think. Okay, so those of you who probably thought that A may have a bigger force than B is probably because you thought, well, A has a much bigger charge, right? It's going to push B with a bigger force, right? But remember Coulomb's law both has, right, the force electric, right, this constant. It takes the magnitude of Q1, magnitude of Q2, right, divided by R squared, right? So E, right, A is Q1, B is Q2, right? But if you're trying to calculate the force that B on A, right, let's do that in orange, right? B is 1, A is 2, but when you multiply those two numbers together, what would you get if they're, even though they're different charge? They're going to get the same number, right? So like 4 times, so 4 times 16 is the same thing as 16 times 4, right? It doesn't matter which one you multiply together. So those of you who figured out that they actually do exert the same force in each other, right? Either got this from this equation or went back to your general physics 1 knowledge and said that if I push Anthony with a 10 newtons of force, he's going to push me back with 10 newtons of force, right? That's actually Newton's third law. Okay, so hopefully both those interpretation make sense. Okay, any questions before we move on to maybe a 2-dimensional example? Okay, let's see how much time we got. So one thing, so especially those of you who are taking the class from me the first time, this book also has a lot of really good examples. Okay, so make sure you guys are going through these examples. You know, and that gives you a lot of practice on how to do the problems in both mastering physics and give you practice on the exam. Okay, and one of the things I talked about last semester is that this is the way I think, you know, we should use the examples, because the examples are kind of like you only have a limited number of examples, so you want to utilize them the best possible way. So the way I would use this example is by basically just kind of read the example problem, but don't look at the solution, meaning you just look at the problem itself, just, you know, this piece, right? Okay, and don't look below it. Don't spoil yourself. Okay, and then work through the problem by myself using my own knowledge. Okay, you may get stuck or you may get the problem wrong, but that's actually a very good thing. If you get stuck, that means there's something that you need to know that you don't know, right? So you can either go back to the lecture notes, the lecture videos, or read the chapter again and figure out, okay, what was I missing? How come I didn't understand how to calculate, you know, the repulsion force between these two things? What constant was I missing? Okay. Once you get to the answer, right, check the answer with the solution that it gave you, okay? Right, because the example gives you the solution, okay? If you got it right, don't just say, oh, I got it right, so I got this. So I don't have to worry about this anymore, right? Still read through the solution and see if there's any difference between the way you did it and the way the book did it, right? And there may be like a shorter way. So sometimes, especially on an exam, a lot of times we expect you to do the problem the shortest way possible. There may be a shorter way that you didn't realize, oh, I did like 10 pages of algebra that got the same answer, but then the book did it in like 3 lines of algebra somehow, right? So that's, there's a lot of shortcuts sometimes you may not realize. If you did not get it right, that's actually a very good thing because, right, that way you can actually use these examples to train yourself so that when you do see this type of problem on an exam, you will get it right. Because, right, if you don't get it right the first time, what you want to do is read through the solution and figure out where the first point where you got something different from the book, right? And that way you can try the problem again. Now you have that additional knowledge. Oh, instead of multiplying those 2 numbers together, I should have divided them, right? So, and then you can take yourself through that step, fix that one little problem and see if you get the answer right, okay? If you don't still, then go back to the next step and see where you went different, where your solution is different from the book once again. So you kind of iteratively, right, get to the right answer, okay? The more you do this, the better it is, okay? Any questions about this before I do the other example? I know most of you guys are not going to follow it like a couple of times, okay? And trust me, it is very helpful, okay? I still do this myself right now, okay? Okay, so let's finish up with some examples on how to use Coulomb's law. So in fact, I'm going to spoil example 22.5 for you guys, where it's a 2-dimensional problem with 3 charges. So this gives you guys a good sense of what we're going to practice on tomorrow in the worksheet, and also what some of the homework problems going to be on, okay? Okay. So we have this problem where we have 3 different charges. They even gave us a diagram, which is really nice of it to give us a diagram, right? But it's not necessary, okay? A 3-charge particle, Q1 is negative 50 nanocoulomb, Q2 is positive 50, and then Q3 is positive 30, okay? And the distance that's given between them are given here is in the rectangular box, okay? So what the problem is asking us to do is calculate the net force on charge 3. Okay, this is charge 3. Okay, all you have to, so what charges are applying the forces on, which charge are applying for a force on charge 3? Which numbers? 1 and 2, right? So those are the only 2 forces, charges that are applying the forces, okay? So one thing to be careful about is that sometimes what happens is that you guys will jump into the equation and just start writing down Coulomb's law, and then Q1 and Q2, right? And okay, I'm going to demonstrate how this could happen, okay? So we're going to try to figure out what charge 3 is doing, okay? So charge 3 is going to be attracted to charge 1, right? But then repulse, let's do that in green so it matches what's on there, blue, right? It's going to be attracted by this, but then repulsed by charge 2, right? So the net force on it is going to be like something between the 2 somehow, right? So in fact, I'm going to redraw this, okay, with a free body diagram with my information gathering piece. I'm going to do the free body diagram on charge 3, okay? So charge 3, when you do a free body diagram, whatever object it is, you just make it into a dot, okay? Charge 3 is going to have a force from charge 1 pulling down on it, okay? And it's going to have a force repelling it away from charge 2, right? 2 on 3. Notice that both these are 3s, right? Because we're only trying to figure out what the force is on charge 3. The net force, let's do that in green, okay? The net force is going to be something like this, okay? On charge 3. Do that. Okay. I don't know what the magnitude is, so I'm not sure how it's going to add up. So maybe it's going to be a little bit shorter, right? Maybe like this, okay? Right. So that's what I expect the net force to be. I'm going to declare an X and Y axis. I'm going to make X horizontal, Y vertical, okay? So maybe it's obvious for this problem, but sometimes, you don't have these horizontal and vertical axes, right? Okay, so now what I'm going to do, I'm going to take this to the concept connection, right? So we're going to need to apply Coulomb's law. How many times do we need to apply Coulomb's law? Twice, right? Twice. And add the two forces together. I'm going to note this. They are going to be vectors. So vectorially, maybe it's spelled that way, to get the net force, right? Okay. So basically me drawing that diagram, right, is I'm restating what I just drew on the diagram, okay? So now, right, I'm a little bit out of space. So let's do this on the right here, right? So I'm going to try to figure out what these two forces are, right? So let's try to get force 1 on 3, okay? So what's the magnitude of that force, okay? Okay, so it's K, Q1, Q2, that's the formula, right? Right. What's Q1 in this case? What should that be? Charge 1, yes, okay, great. Which is, right, it has the magnitude, so we're just taking the absolute value of it, -9, okay? And what's Q2? Charge 3, right? 2 corresponds with charge 3 because that's actually what's being acted upon, okay? So these indexes you have to be very careful about, and don't just assume, 1 corresponds to 1, 2 corresponds to 2, okay? So this formula applies to no matter what the indices are. So you may have a situation where the index still match up just like this, okay? And R, how do we figure out what R is, okay? R is, sorry, this is the 1 and 3. R is 10 centimeters, right? So that's actually 0.1 meters square, okay? Right, so that's going to be equal to, let's see if I can do the calculator thing again. Times 30 e to the -9, all divided by 0.1 square. Okay, so I got a force of 1.348 times 10 to the -3 here, right? Okay, and if I want to know what the direction is, right, I go back to the diagram. I expect the force of 1 on 3 is going to be in the negative j hat direction, right? This is going to be in the negative j hat direction. It's going to be pointing downward. Okay, I'm going to need a little bit more space, so I'm going to push the stuff below a little bit further. Okay. All right. So that's the easier one. The harder one is going to be this piece, okay? Because it's going to have some x component, it's going to have some y component, right? So force of 2 on 3, okay? I'm going to find the magnitude once again. So we put in K, Q1, Q2, right? All magnitude divided by R squared. Okay, if you plug that in, I'm just going to skip kind of the step. So these are the same charge actually. It's going to have the same magnitude times 10 to the -3 Newton, but the direction is going to be different, right? It's going to point to the top left, right? So how do we figure out that? How do we figure out the components of this thing? Okay, so I'm going to do this little drawing on the side. Okay, right. So we know that this is the vector 2, 3. Okay, so it's going to have some x component to it and some y component to it, right? How do we figure that out? Okay, so this completes a triangle here, right? If we can figure out what theta is, right? If we figure out what theta is, then, right, the x component here is just going to be the magnitude of 2, 3 times cosine of theta, right? because this is the adjacent over the hypotenuse. Okay, but the problem doesn't tell you what theta is. Anyone has an idea how to figure out what theta is from this drawing? Right, from the drawing, this is 10 centimeters. This is 5 centimeters, right? I'm sorry. We're trying to get to the force, but we don't know what the angle is on the force, right? But I have the magnitude of the force, right? So there's two things in this equation I need to get, right? I know I can get this, right, from this up here, right? But I'm missing this little piece, right? And the left-hand side, I don't know at all, right? So any idea how to get to this theta? Anyone? Yeah. Inverse tangent of what? I'm sorry? 10 over 5. Why 10 over 5? Right, because you have this right triangle here, right? Right, the tangent function tells you the ratio between the opposite over the adjacent, right? Tangent, if you want to do your SOHCAHTOA thing, right? Tangent of an angle is the opposite over the adjacent, okay? We know the length of this triangle, right? Even though it's, so the length of these, right, allows the similar triangle compared to the force, so therefore they have the same angle. So therefore, the opposite length, right, is 10 centimeters. In fact, I don't need to convert it to meters because the units are actually going to cancel out, right? So theta is actually inverse tangent of 2, right, as just said. Okay, I'm going to do this in degrees, inverse tangent of 2. And that's going to be the calculator trying to do an exact number for me. It's going to be 63.4 degrees, okay? And hopefully that makes sense, even though I didn't draw it right, right? You expect that, oh, this is 10, this is 5, it's going to be bigger than 45, right? Okay. So therefore, now we have this theta, right? Now we can actually compute, right? What this number is, put it in here, theta put in there, okay? 1.348 e-3 times cosine of the previous answer we got. I'm just going to copy that. Okay. So the x component of force 2.3 is actually 6.03 times 10 to the -4, and that's going to be newtons. The y component in this case, right, it's just going to be the sine theta version of it. So 2.3y is going to be, change this over to sine. (1.206 times 10 to the -3 newtons. And still, we don't have the answer yet, okay? The answer is actually the net force, right? We have to add both of these forces together, okay? The net force, okay, what we need to do is add the x component of force 1.3, right? And that will give us the I hat direction, plus add to that, let me just do it on the right-hand side. Similarly, 2.3 in the y direction, plus force 1.3 in the y direction. That gives us the j hat, right? So 2.3 is up here. What 2.3 is what we actually calculated, right? We fill that in here, right? Let's do that in purple, so I don't have to recopy all the numbers, right? The y part is over here, right? And then I'll do this part in orange, right? I know that the vector 1.3 only has a y component, right? It's actually negative. So that actually goes down here. But what about the x component of force 1.3? What should that number be? 0, because it has a 0 component, right? Okay, great. So this x component here, we're just going to copy that because anything add to 0 is still 0. Sorry, anything add to 0 is just anything. Okay. And then the y component, you actually have to do a little calculation to add them together. In fact, right, so this is a negative number, right, because of the negative j hat. So you actually have to subtract those two numbers. Okay. 348 e to the -3. Okay. This is actually going to be negative 1.42 times 10 to the -4, and that's going to be in newtons also. And I made one mistake. Who spotted my mistake? Yeah. Oh yeah, the distance are different between the two. So yeah, so this number is actually force 2.3 is actually different. So let's fix that real quick. Okay, good catch. So the distance between them, right? You have to actually calculate what this distance is. Okay, so this is going to be 5 squared plus 10 squared, all square rooted, just from Pythagoras theorem, plus 10 squared, all square rooted. The distance between them is actually 11.18 centimeter, or 0.112 meter. Okay, so the number is actually slightly different, but I don't think it was worth it for me to go back and do everything. But there is another mistake that I made that hopefully other people can catch. Okay, any idea? So when I draw this vector, right, it's going to point to the left, and I wasn't sure if it's going to be higher or below, above or below the x-axis, but this part tells me that, right? But what should the sign of the x component be? Positive. It points to the left. Yeah, so I didn't take into account this negative sign in here. Okay. So I think these numbers are going to be slightly different from compared to what's in the book, but that's because there's going to be like a 10% difference from the distance that I forgot to change when I calculated the difference between this force and this force. Okay. All right. So it's good. So there was one mistake I made on purpose, one mistake I did not make on purpose, which is good. Okay. So that's why you want to go through these examples and see where you differ from the example and figure things out. Okay. Okay. So I'm going to take the last few minutes just to introduce kind of like the last idea of this chapter. It's this idea called the electric field, and I'll do the example tomorrow. Okay. The electric field is a way for us to figure out if you have a single charge. So let's say right now what we've been doing, right? We have some charge A and some charge B, and we can figure out the force that A is exerting on B somehow, right? Okay. But what if I take this charge and move it over here, right? Let's say I move charge B over here, right? Now the force is actually this way, right? Let's do that prime, okay? Okay. So you can see that it's kind of annoying to every time you have charge A, every time you move charge B, you have to recalculate everything, right? Just as what we happened up here, right? Well, on our previous example. What happened is that what you can do is have a concept of what's known as an electric field, where we just have a field that permeates through space, right? And if this is a positive charge, this field will go outward. And you can see that, right? When this field reaches charge B, it basically points in this direction that the force is going to apply to charge B, right? Right. On this case, right, on this field, right, this also points in the same direction as the direction that force A, charge A is going to apply to force B. So you can see that if you map out this field in the first place, no matter where you put the charge, it's pretty easy to calculate what the force is, right? Because you already have the direction, and you just need to figure out what the charge B is. So the concept of the field is kind of nice because what it allows you to do is you take a single charge source. You basically think of that as the source of the electric fields, the electric force. And whatever charge you put a charge here, we know it's going to go in this direction. You put a positive charge here, it's going to go in this direction. You put a positive charge, it's going to go in this direction, right? So that's for a positive charge source, okay? Electric field source. All the rays kind of go outward from it. But you know that if I put a positive charge here, right? If the central charge is negative, right, it's going to go towards it, right? So the electric field actually goes towards the negative charge. Okay, so the idea is that the electric field, let's just write this down. And this is just something that, physics made up, just for us to do like a little bit easier math with it, okay? Basically radiates, oops, from positive charge, okay? And then converges on negative charge, right? So that's sort of like the English description of these two diagrams, okay? So when you guys think about a positive charge, think about it having like all these rays of electric fields emanating from it. If you have a negative charge, all of these rays of electric field goes towards it, okay? So that's the idea you want. That's the picture you guys want in your head when we start working with electric field. And I'll go through the example tomorrow as opposed to today, okay? So that's all I have for you guys today. Tomorrow we'll do a short, 15, 20-minute lecture, and then we'll have time to do the worksheet again, okay? Stop recording.